In this video, we'll talk about piecewise defined functions, and in particular, we're going to be looking at graphs of piecewise defined functions. So let's go ahead and talk about an example and kind of relate this to what a piecewise defined function is. So a piecewise defined function is basically a function that's been defined in two or more pieces. And you see this a little bit in the real world where you're trying to model a function, and after you reach a certain point, the function changes. And one such case would be a carrying capacity. If you're talking about population, population is going to probably grow until you hit a certain point where the environment or the ecosystem cannot sustain anymore. So at a certain point, the population cannot grow anymore. So that would be one example of how conditions can change, meaning that your function has to change to reflect it. And sometimes it can be a really jarring, jagged change. So a way that we can write this is, as an example, y equals 2x when x is greater than or equal to 1. So when x is 1 or more, I use this. If I'm looking for less than 1, y is going to be x minus 1. So I will draw this in two colors to kind of iterate the point. Now, it's a little strange trying to make a t-chart for this because technically you have two functions and you're trying to kind of smash them together, for lack of a better term. So the way I do this, and it might seem a little strange at first, is I draw kind of like a double t-chart. So I'll have x, and then I will put the one of the functions in, and I'll actually write out the expression for myself. And then I will also do the other one, x minus 1. So if I'm relating this to a coordinate grid, what I'm gaining from right here is that at 1, something changes. So I tend to draw just kind of a vertical line for myself. That's basically, if I'm looking at it, if I was to just graph 2x, 2x is going to be over here. So if I just cut it off at 1 and laid it over a graph of x minus 1, that's essentially what I'm doing. And there might be a bit of a jump or a bounce or something, but that's okay. So what we're going to do, and it might seem a little strange at first, but I'm going to plug 1 in first. That's kind of my boundary. Now I know it goes into 2x. So 2x, I would plug it in. 2 times 1 is 2. Okay? And I'm going to go ahead, and it might seem a little strange right now, but I'm going to put a solid dot there. And I'll explain why in just a minute. And then the next thing I'm going to do is I'm actually going to plug this 1 in to my blue function as well. And that might seem a little strange, but bear with me here. So I take 1 minus 1, which is 0, and I'm going to put a hollow dot kind of up in the corner there. Now, the reason I did that is that if I say I wanted to plug in x being 0.99995, I would technically use the blue expression still. So I'm going to go right up to the 1 without actually using the 1 in my graph. And we have a way to represent that with our graph. So the idea is we're going to use this open dot to kind of show, okay, I go through 1 and 0. Well, I don't actually go through, but I get right up to that value. And that means I can still connect the line, so I can treat that almost as I would a point. And likewise with the 2 there, that one's a solid dot because I do know that it is included there because of the equal to here. And this might seem a little weird, and it is. It really is. These are kind of bizarre examples, but bear with me here. So once I have this boundary established, the idea is I need 1 to the right and I need 1 to the left. Very similar to what we did with the absolute value, except I don't have to find that boundary. I don't have to figure out where it changes. It's going to tell me in the equation. And the only difference with the solid dot and the open dot is that if there is the possibility for it to be equal to, it will be a solid dot. If it's strictly less than or strictly greater than, then it will be an open dot. So now I get to pick. And again, let's pick convenient values. There's no point in plugging in x equals 52 unless 52 is convenient. So I need a value. Let's go ahead and do less than 1. I'm thinking an easy one would be 0. Now, there is no reason to plug it into the 2x because it doesn't really apply. So I'm only going to plug it into the x minus 1. So I take 0 minus 1, which is a negative 1, meaning that I go through the point 0, negative 1. Now, since I know this expression, this blue expression is linear, I can just go ahead and draw my curve, or not curve, the line. So there's the left half. There's x minus 1 up until 1. And basically I'm just I'm drawing that piece of the graph. It is x minus 1 until x hits 1, and then the conditions change. So now I'm going to pick something greater than 1. And I'm thinking, okay, the next easy value I can think of is 2. No need to get fancy with it. So I'm going to plug 2 in to 2x, and I'm not going to bother about plugging into the blue expression. So then it goes to the point 2, 4, which let's say that's up here. And then I'm going to plot this again. I know it's a line, and it's going to take off like that. Now this would be a graph of this piecewise defined function. And it looks a little weird, but it is that whole idea of it hits a certain threshold and then things change. And that happens when you're talking about graphs or equations in real world situations. Sometimes you hit a certain point and things will change pretty drastically. So that's where these things are useful. However, doing mathematics with them is kind of, messy, I guess, for lack of a better term. So bear that in mind. This is something that maybe is not so much drilled in during a lot of math courses, but it is something that's worth being aware of. These things are very applicable, and the reason that we don't talk about them a whole lot in math courses is that we really worry more about the pieces themselves. So any math that you could do with, say, y equals 2x or y equals x minus 1, you can do with this piecewise function. It's just going to apply to only where those functions apply. So there's a video on piecewise functions and kind of a justification for how they're useful and where they go. They are kind of tough to graph, so just bear that in mind. You're going to want to plot both of those boundary points regardless, just so that you know where the solid dot and the hollow dot goes. And then after that, you're going to pick a point to the left and a point to the right of that boundary. If you're talking about lines, you're only going to need 3 pieces. And for most textbooks, they usually only worry about linear piecewise defined functions. Usually.